Hello again everybody, thank you for joining me in what is the first in a series of videos for Year 13 pure A-level maths. So it starts off this chapter 1 being about proof and algebraic division and later partial fractions. You'll notice I'm going to split the first subchapter, which is about proof, into two parts. So I'm going to do it as 1.1a this video, and I'm going to give proof by contradiction a more in-depth video all on its own in 1.1b. So in 1.1a, towards the end, we'll touch upon proof by contradiction, but because proof is a topic which students tend to struggle with perhaps more than others, I thought it would be worth it having the respect of having two videos rather than just one to allow for more deeper understanding, as it were. Anyway, enough of me prattling on. Let's have a look and get warmed up with some warm-up questions. So as usual, there's 4, same job here. So have a go at these, press pause now to try them on your own, and then press play to see the solutions step by step, and hopefully yours match mine. Okay, so assuming you've done that, let's have a look at the solutions to question 1. Question 1 is just a list of 6 descriptions, and on the right hand side 6 algebraic representatives for each. So it's just a case of underlining or matching up with arrows which goes to the correct one. So first of all, the product of 3 consecutive integers, that's going to be k, k minus 1, k minus 2. So k be the largest, k minus 1 is 1 less than that one, and k minus 2 is 2 less than the largest. So if k were 8, it'd be 8 times 7 times 6, or 6 times 7 times 8, if you read it the other way around. An odd number is going to be 1 more or 1 less than an even. So an odd number is going to be 2k minus 1. Another representative which people tend to find easier for an odd number is 2k plus 1. However, 2k plus 1 sort of skips over the first odd number. If you go for k being defined as just any natural number, if k were 1, then 2k plus 1 starts off as being 3. So you're going to go 3, 5, 7, and so on. Whereas 2k minus 1, starting off with k being 1 and k being a natural number, 2k minus 1 covers all the odds from 1 upwards. So that's why 2k minus 1 is my favourite representation, although almost always, in fact always, unless the examiner says explicitly otherwise, 2k plus 1 is going to be a valid algebraic representative too for an odd number. Okay, so carrying on. Even number. This is easier, really. I probably should have put even before odd, but an even number, I'm hoping you'll agree is obvious, is going to be just 2k. Because an even number is just any integer, any natural number multiplied by 2. A multiple of 3, hopefully in a similar way, it's just as easy. A multiple of 3, we can say is 3k. One more than a multiple of 3, we can say is 3k plus 1. In other words, if you imagine this as a fraction all on top of 3, that'd give us k plus 1 over 3. So in other words, 3 wholes and 1 remainder when divided by 3. In the same way, 2 more than a multiple of 3, finally, to finish off, is going to be 3k plus 2. In each of these cases, it should be said that k is a member of a natural number set. Warm-up question 2. We have a formula for the nth triangular number, or sometimes just called triangle number, t subscript n. It's given by t subscript n is a half multiplied by n plus 1. So let's prove that the sum of 2 consecutive triangular numbers is always a square number. And for this, we're going to pick 2 valid algebraic representatives for 2 consecutive triangular numbers. So the sum is just going to be obviously 1 plus the other. So if I just pick the general t subscript n as the first one, and the larger consecutive one as t subscript n plus 1, then using this formula here, t subscript n is just the same as this thing here, half n, n plus 1, and then t subscript n plus 1, the n here becomes n plus 1, and this n plus 1 is now n plus 1 plus another one, which is n plus 2. So get your head around that first, and then let's proceed. This isn't obviously a square number yet, so what we could do is expand out both of these sets of brackets. That would then give us a half n squared plus a half n from this bit in blue, and from the bit in green, we're going to get half n squared, then plus 3n over 2, or 3 over 2n, because if we did FOIL or use the grid method, whichever you prefer, we'd get 3n, but it's half of all of those terms. And finally, the constant term, 1 times 2 is 2, but half of 2 gives 1. We can now simplify this, which gives us n squared plus 2n plus 1. And this is a relief now, because now you should notice this is a perfect square. This factorizes into n plus 1 brackets n plus 1, or more naturally, n plus 1 all squared. So because n is a natural number, n plus 1 of course is a natural number, so this represents a natural number squared. In other words, this proves that we're going to always get a square number. We now just need to conclude with a finalizing statement to just verify that we're complete. Something along these lines I think is fine. Therefore, the sum of two consecutive triangular numbers is always a square number. Sometimes it's not always clear if you need to say this concluding statement or not, so I think the best course of action is, if in doubt, to always include a worded concluding statement, which just shows to the examiner that you know what the final algebraic representation means, that you know that, for example, this is sufficient. Question 3. Again, by using the appropriate algebraic representatives, just driving home the point that this sort of first of the two chapters on proof, this is a warm-up to get you stronger for 1.1b. Anyway, prove that the product of two consecutive odd numbers is always odd. So I've highlighted the fact that these aren't just any two odd numbers, these are two consecutive ones. So if we're going to use algebraic representatives, consecutive means they are inherently linked to one another. So whatever letter or symbol we pick for one, we should really be using that same symbol for the other, plus or minus, of course, a difference of 2, because the odd numbers, consecutives, always have a difference of 2 between them. So to start off with, for part A, I'd suggest start off defining some natural number k as being an element of a natural numbers. So in terms of symbology, you could write this. Looks like Ken, which always tickles me because I'm still very immature. All this means is k is a natural whole number. So 2k plus 1, that's a representative for a odd number, like I mentioned in warm-up question 1. The next one will be 2 higher. So this is a smaller one. This is the next odd number, the bigger one. So doing it algebraically, expand these brackets, we get 4k squared plus 8k plus 3. We're wanting to show that this is always odd. The best way I think of conceptualizing an odd number is that it's one more or one less than an even number. So let's try and factorize out a 2 here and prove that what remains is an odd number. So if I factorize out here either a 2 or a 4, either's fine. 4 brackets k squared plus 2k plus 3. And so what this says here is that this is 3 more than an even number. It's fairly self-evident that a multiple of 4 is even. Therefore, this is odd. Another way which I'd normally do, actually, I'm surprised I've gone for this way. I'd normally factorize out the 2, which in my mind really emphasizes the fact that whatever thing we have here is even because you factorized out a multiple of 2. So if you're trying to find something or trying to prove something is even, you could just factorize out the 2. That would always work as well. Part B is similar, but part B now we're saying any 2 odd numbers. So whereas before we had to use the same letter that ties them together, now we need to use different letters because the question explicitly is saying these are just any 2 which don't really link in any way, shape or form. So for part B, I should always conclude as well with part A, like I say, to conclude, therefore the product of 2 consecutive odd numbers is always odd. So part B, let K and L represent different, non-tied together or not linked natural numbers. So a representative for the first odd number using K would be 2k plus 1. Representing an odd number using L could be 2l plus 1. So the product of one and the other, just put them both in brackets and expand out. We get 4kl plus 2k plus 2l plus 1. Again, to prove that it's always odd, I want to emphasize it's one more or one less or any odd number different to an even number. So if I look here, all these terms are even, so I can factorize out a 2 from here, which gives me this. 2 lots of 2kl plus k plus 1, then finally that plus 1 on the end. This is perfect. This here is some whole number multiplied by 2, so this thing here is all clearly even, Anything even but one bigger will therefore be odd. So just carefully conclude with words. Say something like, this is one more than an even number, which is therefore odd. Therefore, the product of any two odd numbers is always odd. If you're wondering what these little squares mean here, this is just a fairly old-fashioned now way of concluding a proof. This is like a big full stop. It's equivalent to saying QED, which is an abbreviation of Latin, which just means that the proof has been completed. Finally, warm-up question 4. Find the coordinates of a turning point of the curve with equation y equals 3x squared plus 8x minus 4. Now, I know that you know that this can be done with a calculator, but if you want to be hardcore and just do it old school, algebraically, let's complete the square. So we start with y, which is 3x squared plus 8x minus 4. Factorize out the coefficient of x squared from any terms to do with the x. So if we factorize out the 3 from the x squared and the 8x term, we get 3 lots of x squared plus 8 over 3x, and that minus 4 we can just leave on its own. Now, the stuff in the brackets, we now can complete the square with this. So the x squared becomes an x, we half the coefficient of the x, which gives us 8 over 6, but 8 over 6, of course, is just 4/3. So remembering it from GCSE, even, the next step is, inside some big squared brackets, whoops-a-daisy, that's my mistake, that should say squared, minus 16 over 9, all minus 4. And again. So, expanding out these squared brackets, we now have 3 lots of the curved brackets squared. 3 lots of minus 16 over 9 gives minus 48 over 9, then of course minus 4. And then finally, minus 48 over 9 minus 4 can be simplified further into just minus 28 over 3. And again, that should be a squared here too. Then finally, just remembering the significance of this number and that value as well, we've essentially got what the turning point of this curve is. So therefore, the turning point of this curve is this value with its sign switched, minus 4 over 3, and the y value at the turning point is just this value exactly as is, minus 28 over 3. So after those warm-up questions, hopefully you're a bit more familiar with just the old school algebraic manipulation, because sometimes we can lose sight of that when we're so heavily reliant on the calculator and assuming old knowledge is there, which of course it should be so long as it's used, and this is a good opportunity to do so. And we need to be really fluent, strong and fresh with these skills for realizing and understanding deeply what proof by contradiction is and when to use it and how. So let's have a look now at a bit more proof, and to start off with, we're going to still be in the vein of revision and just recover some of the proof methods and topics we saw in year 12. So far, algebraic proof, AS level, year 12, what have we seen so far? Well, we've learnt about some methods of proof already. The year 12 AS section of the course introduced a variety of methods, most importantly, proof by deduction, which is just another way of saying algebraic proof, really. I mean, proof by deduction underpins everything. This, in my head, is just an algebraic proof, like the warm-ups. Proof by exhaustion is another one. That's where there's only a certain number of finite cases to prove, if I'm speaking properly. Don't know what's wrong with me today. So you prove them all exhaustively. If you prove them for every single case that there is in a finite list, you've proven for all cases, therefore proven what was to be proven initially. And proof by counterexample, as it says really, you have a statement, you show it to be wrong by showing that it's incorrect for some other value which is a valid choice to use. So let's have a look at these in more depth in a second with some light practice too. Before that though, you need to remember proof by deduction, like I've said, is essentially just proof using well-established obvious number facts using algebraic representatives to arrive at the required results. So it underpins all A-level proof. Sometimes though, the required deductive steps are either not available or not obvious to us. In those cases, we need to work backwards until we arrive at what the textbook says, I think it does anyway, and what I've ended up saying myself anyway, is a statement of truth. So sometimes, with awkward proofs, you need to begin from a result or a fact that is obvious or so very simple to demonstrate, you can get away with just saying, here's my starting point, I'm not going to even show this is true because it just so obviously is. And then from that so obvious trivial starting point, then work forwards from that point to get to where you want to go to. So the last one is almost working in reverse. You go backwards and then reverse back again on yourself, which I'll show you in a second. So here's a summary of them anyway. So proof A, proof by exhaustion. Proof B, a very simple proof by counterexample. Proof C is a proof by deduction, which I've said we can also essentially say is an algebraic proof. And proof D, even though proof D would not say in a question, give a statement of fact, this is one where we're going to have to sort of work backwards from a statement of fact to arrive at this. So the actual proof for this question might just simply be something like prove for x is any real number, x squared plus 8x plus 10 is at least as great as 2x plus 1. So let's have a look at these step by step. So proof A. A sequence is defined as t subscript n is 2 to the power 2n minus 1 for n being 2 or greater. We're going to prove by exhaustion that this is going to be a prime number for all of n from 2 to 4 inclusive, where n is any natural number. This isn't going to be a very exhausting proof by exhaustion, because if you think about it, there's only 3 cases. N is 2, n is 3, n is 4. So let's do this step by step. So first of all, when n is 2, Tn is going to be t subscript 2, which is going to be 2 to the power 2 times 2 minus 1, which is 2 cubed minus 1, which is 8 minus 1, which is 7, which of course is prime. When n is 3, that's going to give t subscript 3, which will be this expression here. This of course means 2 to the power of 6 minus 1, which is 2 to the power 5, minus 1. 2 to the power 5 is 32. 32 minus 1 is 31, which of course is prime 2. If you want to check it, you can do. And finally, when n is 4, we have this expression. This is essentially the same as saying it's 2 to the power 7 minus 1. 2 to the power 7 is 128. Minus 1 from that, we get 127. And again, this number is also prime. Therefore, we've shown it's prime for 2, 3, and 4 as needed. As I've said before, probably a good habit to always conclude with a worded summary. Therefore, t subscript n is prime for all of n between 2 and 4 inclusive, where n is any natural number. So in the concluding statement, you're almost repeating what it's saying in the question. Proof B. So exactly the same sequence here. Tn is still the same as above. Don't have to put it twice. Where n is 2 or greater. Prove by counterexample, but it's not always prime. So we've done it for 2, 3, and 4. Let's just go for the next one up, when n is 5. T subscript 5 is 2 to the power 2 times 5 minus 1, which is 2 to the power 9 minus 1. 2 to the power 9 is 512. Take 1 away as 511. However, if you check that on your calculator, you should see that is actually a multiple of 7. It's 7 multiplied by 73. If you really want to think of it this way, you could also think of it as it's a multiple of 73. Either way round, it's clearly not prime, because we can split it into 2 separate factors. And again, my suggestion would be to always conclude with a worded summary or conclusion. So t subscript n, therefore, is not prime for all n 2 or greater, where n is any natural number, since we've just shown that t subscript 5 is not prime. Proof C, just a simple algebraic proof really. The difference between the squares of any 2 consecutive even numbers is always going to be a multiple of 4. So for this one, I'm just going to write out to make it clear. You don't really need to do this. This can be assumed by the examiner. The first even number I'm going to call 2n, in other words, just some multiple of 2. And the consecutive one will be 2 bigger than that. So the larger even number, which is consecutive to the first, will be 2n plus 2. And to find the difference, that's just one value subtracted from the other. normally the larger value subtracted from the smaller. But it's not the difference of these consecutive even numbers, it's the difference of the squares of them. So the next step is to do 2n plus 2 squared minus 2n squared. So this is what we have. So from squaring out 2n plus 2 all squared, we get 4n squared plus 8n plus 4, then minus off 2n all squared, of course, is just minus 4n squared. The 4n squareds will cancel, just leaving us with 8n plus 4. We want to show this is a multiple of 4, so we factorise out the 4 and show that inside the brackets we have a whole number. N is a whole number, this is going to be an even number, plus 1, so it's going to be an odd number. So it's a 4 lots, a multiple of 4, of some odd number, 2n plus 1. So we've proven it, but again, what I would suggest is to always conclude with a worded statement. So, therefore, the difference between the squares of two consecutive even numbers is always going to be a multiple of 4. Finally, proof D, and again, like I've said, if this question were asked, it would normally just say prove algebraically or prove deductively or something like this that this statement is true. It would not mention a statement of fact. I've highlighted this in green just as a hint that this is one of those types of questions. But by the end of this chapter, you need to be quite familiar yourself spotting when it's one of these or not. So anyway, this obviously isn't too clear yet. I mean, this could be positive, this could be negatives. So we need to start from a simpler point. So going back to GCSE, the hunch would be to get one side equal to 0. So that's what we're going to do. So let's start with exactly what we had, x squared plus 8x plus 10 larger than 2x plus 1. If we subtract 2x plus 1 from both sides to get the right-hand side equal to 0, we get x squared plus 6x plus 9 is equal to or greater than 0. This now is a perfect square. It factorises into x plus 3, x plus 3. So this becomes x plus 3 all squared is equal to or greater than 0. And this is a statement of fact, because we know from GCSE or even before really, that if we take any natural number and square it, it's got to be at least 0. A minus multiplied by a minus comes out to be positive. A positive multiplied by positive again is a positive. It can never be less than 0. The only way it could be 0 itself is if what's inside the brackets is precisely equal to 0. So we don't need to state that because that is fairly self-evident. So we can begin from here and work backwards to prove this initial statement. So this here would be just what I would do almost in rough work. This would be not in the margin as such. I'm not saying don't write this down, but this is like informal working to get you started off formally. So this is the formal starting point. So starting from this point, we now proceed. So start with this statement of fact. Expand out to get to this line. X squared plus 6x plus 9 is obviously therefore follows from this statement of fact. That's got to be equal to or greater than 0 too. Finally, add 2x plus 1 to both sides, and we've got what we wanted to prove. Therefore, x squared plus 8x plus 10 is larger than or equal to 2x plus 1. So that concludes, in a very brief summary, what we should have learnt from AS or Year 12 last year. Moving forward, it's worth considering in a bit more depth subsets of a real number line. So understanding the key properties of real numbers is fundamental to deeply understanding the logic of proof itself. The set of real numbers, which is this double-struck capital R symbol, can be thought of as being divided into two subsets. The rational numbers, which is a capital double-struck Q, and the irrational numbers. So a number is either rational or it is not. As simple as that sounds, it's worth stating anyway. A number is either rational or, if not, it is irrational. It can't be both at the same time. So thinking of irrationals first, the rational subset, capital Q, will also contain all the integers, capital Z, within it. So in other words, because Z is entirely included within Q, we say that Z is a subset of Q. All of Z falls within Q. Going one step further, since the set of all integers necessarily contains the set of all natural numbers, in other words, just the positive integers, It's also true that the natural numbers is a subset of the integers. The natural numbers is essentially just half of all the integers. The natural numbers is the positive half of the integers. So putting all of that together on a number line, we could express the division or the partition, maybe I should say, of a number line as the natural numbers are a subset of the integers. The integers are a subset of all the rational numbers, and all the rational numbers, again, are a subset of all the real numbers. So everything falls within the subset of real numbers if you're doing A-level maths. However, it's also true that the real numbers are also a subset of a set of all complex numbers, capital C. So if you want to be a bit more sort of developed about it, or if you're doing further maths or just out of interest, then this is all included within the subset of complex numbers. Closure under the laws of arithmetic. So it's useful, although not strictly necessary, to be familiar with the vocabulary of closure when it comes to sets of numbers. It just helps to understand the whys and hows a bit more deeply. So you don't need to mention about closure in your exam, but it's still, in my opinion, definitely worth knowing about. And for that reason, amongst many others, I've split this chapter into two to go a bit more in depth. So about closure, for example, we could say that the real numbers are closed under the operations of addition, subtraction, and multiplication. In plain English, that just means if you have two different real numbers, R1 and R2, then real plus a real will give a real number. Any real number take away a real number, again generates a real. And a real number multiplied by a real number, again, will give you a real number. However, the real numbers aren't closed under division because of the pesky element 0. Divided by 0 is undefined. So partly for this reason, in fact, chiefly for this reason, there's often a set restriction not including the element 0, which is often used to get around this. So including this restriction, the sets of the real numbers, excluding 0, and the rational numbers, not including 0, they're all closed under all four basic operations of arithmetic. The integers, without including the element 0, that's also closed under addition, subtraction, and multiplication, but it's not closed under division, because that only is the case if the larger integer, or one integer, divides cleanly into the other. But for example, if we had 3 and 7, under division we'd have 3 over 7, which although is rational, does not belong to the set of an integers, because 3 over 7 is not a whole number, positive or negative. The natural numbers is closed under addition and multiplication, but not closed under subtraction or division. If you had a small natural number subtract a large natural number, that would take you into negatives. You would get an integer, but not a natural number, and with division, similar, well, exactly the same really to what we mentioned here. That would give a reason why it's not closed under division. So, before we get on to the proof by contradiction step, just finally a few further proofs using representatives. So at GCSE and beyond, students of mathematics are expected to be confident in forming algebraic representatives to construct proofs. So this was touched upon in warm-up question 1, and 2 algebraic representatives were needed for proof C, above which we just did. We now need to consider how to use these representatives to solve more sophisticated problems. A useful strategy for natural number questions that involve checking for divisibility, or multiples of a value or non-multiples, is to consider that the natural number line can be partitioned into multiples and multiples of that particular value. So again, we'd use representatives to do this. So the most easy example of that, in my opinion, are multiples of 2. In other words, the even numbers. Multiples of 2, the evens, can be partitioned into evens, 2k, and odds, 2k plus 1. So we could have 2k, 2k plus 1, 2k plus 2, which would then be a multiple of 2, 2k plus 3, and so on. So writing out numbers like this, the number line would be partitioned into algebraic representatives of multiple of 2, non-multiple of 2, multiple of 2, non-multiple of 2, and so on. Extending upwards, How about for a multiple of 3? Well, for a multiple of 3, we could consider starting off with 3k, which is an algebraic representative of a multiple of 3. 3k plus 1 would be a multiple of 3 with a remainder of 1 if you divided it by 3, and 3k plus 2 is an algebraic representative of a natural number that would leave remainder 2 if divided by 3. The next number up would be 3k plus 3, which again would be a multiple of 3 because we could factorize out a 3. So partitioning like this, multiple of 3, non-multiple, non-multiple, multiple of 3. And again, a subtle point, it's worth noticing as well, that any 3 consecutive numbers necessarily have to include at least one multiple of 3. In fact, precisely one multiple of 3. Any 3 consecutive numbers would have to include at least one even number. Quite obvious, really, but we need to consider these carefully when we are asked questions involving proofs. These two next questions, worked examples, are both from past papers, essentially. One was from a shadow paper, I believe, so these are exam grade questions, and the method I'm going to show you to use is, in my opinion, the most basic, safe to use, tried and tested. So let's now apply this to a couple of exam level questions. So, worked example 1. Prove that for all natural numbers, n squared minus 2n plus 2 is not divisible by 4. A fairly common mistake here is to get caught up in this divisibility by 4 thing and start thinking about multiples and non-multiples of 4. But like I've said before, normally the first consideration is odds and evens. So let's just think about 2 cases first, and if that doesn't work, we can always change our approach. So case 1. What if n was an even number? So if n is even, we need a clear and correct algebraic representative for n, which we should state to make sure we're being absolutely crystal clear to the examiner to assure we get full marks. So let's define n as 2k, where k is some natural number. In other words, n is clearly some multiple of 2. Plugging 2k in for n, we get that n squared minus 2n plus 2, in terms of 2k, is going to be 4k squared minus 4k plus 2. 4k squared and minus 4k have a factor of 4, so we can factorize out a 4 from this expression to arrive at 4 lots of k squared minus k plus 2. And it's worth just saying explicitly, even though it's obvious really, 4 lots of a bracket means this is a multiple of 4, but plus 2, because 2 doesn't go into 4, this means it leaves remainder 2. Or you could just say, this clearly is 2 more, plus 2, than a multiple of 4. Because it's 2 more than a multiple of 4, clearly it's not going to be divisible by 4, because it's going to leave a remainder of 2. So I've proved it for when n is even. Let's have a look when n is odd. Again, we need a representative. So this time let n be 2k plus 1. You could use 2k minus 1 as well, like I mentioned earlier, where k is some natural number. So if I sub this in for n, then n squared minus 2n plus 2 becomes 4k squared plus 4k plus 1, that's the n squared, minus 2n is minus 2 lots of 2k plus 1, and then the plus 2, of course, is plus 2. That simplifies right down to 4k squared plus 1, because that 4k cancels here, that 1 cancels, well, the minus 2 and plus 2 cancel, so let's get the plus 1. 4k squared plus 1, clearly 4k squared is a multiple of 4, but plus 1 means it's 1 more than a multiple of 4. So when n is even, we've got a number which would leave remainder 2 when divided by 4, and when n is odd, we've proven we'd have a number that would leave a remainder of 1 when divided by 4. So either way round, because a number has to be even or odd, for any number you choose, any way round, it's always going to leave some remainder, either 2 or 1, when divided by 4. So to keep it as short as possible, just conclude with one simple sentence now, saying therefore, for all natural numbers, n squared minus 2n plus 2 is not divisible by 4. And if you notice again, in your concluding statement, you're almost repeating the actual question back to the examiner. So it goes full circle. Worked example 2 now. Given again n is a natural number, prove that n cubed plus 2 is not divisible by 8. This time definitely don't get caught up with multiples and non-multiples of 8 unless you want to consider 8 different algebraic cases. Again, the base consideration, let's go odds and evens. First of all, if n is even, again let n be 2k where k is a natural number. In that case, n cubed plus 2 becomes 8k cubed plus 2. 8k cubed, clearly and evidently a multiple of 8, plus 2 means it's 2 more than a multiple of 8, not an exact multiple of 8. So if proven is not divisible by 8 when n is even, you should be able to guess what's coming next. Let's now try when n is odd. So again, we need representative for an odd number. Let n be 2k plus 1, where k again is some natural number. Then n cubed plus 2. Now you might want to use the even binomial expansion if you want to. Or you could do 2k plus 1 multiplied by 2k plus 1 all squared. So this is a shorthand expansion of it. So if you're not sure where this comes from, just brush up on your binomial expansion from year 12, or just expand it out old school by hand. But you should get 8k cubed plus 12k squared plus 2k plus 1, when you do 2k plus 1 to the power 3, and of course a plus 2 at the end. This will now of course factorize to an extent. I want to show about it being a multiple of 8 or not. So what I'm going to do here is actually factorize out a 2. So this is slightly more sort of sophisticated in the approach. You might be panicking thinking you can't easily factorize out a multiple of 8, which of course you can't. But a multiple of 8 has to, by its nature, be even. So by factorizing the 2 out, I get this with a plus 1 at the end, which proves clearly that if n is odd, then this thing here will be odd as well. And if it's odd, it can't be a multiple of 8. So that case needs a bit more deep thinking, but again it comes out cleanly. So we've proven it's not going to be divisible by 8 if n is even, or if n is odd. Therefore we've proven it both ways, so we've proven the thing exhaustively. So therefore for all natural numbers, n cubed plus 2 isn't divisible by 8. One more. This is slightly different, where we have to consider not just odds and evens. So if n is an integer and not a multiple of 3, then n squared is not a multiple of 3. So this time it's being clear about multiples of 3. So odd and even doesn't cover all bases here. So it's saying if n is an integer not a multiple of 3, n squared is not a multiple of 3. So let's just think about representatives of what this integer could be if it's a non-multiple of 3. Well, if it's not a multiple of 3, it's either going to leave a remainder of 1 when divided by 3, or a remainder of 2. So let's go for case 1, where n is 1 more than some multiple of 3. Let's define n algebraically as a representative of 3k plus 1, where k is some natural number. Expanding this out algebraically, we're going to get 3k plus 1 all squared, which is 9k squared plus 6k plus 1. We can now factorize out a 3 from this, which gives 3 lots of 3k squared plus 2k, plus a 1 hanging off at the end. This is clearly a multiple of 3, but the plus 1 means it's going to be 1 more than a multiple of 3. So therefore, if n is 1 more than a multiple of 3, n squared is 1 more than a multiple of 3 too. In other words, if n is 1 more than a multiple of 3, a non-multiple of 3, then n squared is not a multiple of 3. So we've proven it only for when n is 1 more than a multiple of 3. The second and final case, if n is a non-multiple of 3, then n might be 2 more than a multiple of 3. If it's not 1 more or 2 more than a multiple of 3, then it's got to be a multiple of 3. So if n is 2 more than a multiple of 3, I can represent this by 3k plus 2, where k is some natural number. Expanding out 3k plus 2 squared, and otherwise showing what n squared is, we're going to get 9k squared plus 12k plus 4. And again, deliberately factorising out a 3 from this, I'm going to get 3 lots of 3k squared plus 4k plus 1, but 3 times 1 is 3. We've got 4 here, so again we've got the extra plus 1 to add. This is a multiple of 3 quite clearly, but plus 1. So we've shown that when n is 2 more than a multiple of 3, n squared is 1 more than a multiple of 3, hence not a multiple of 3 either. So we've shown it true for when n is 1 more or 2 more than a multiple of 3, which is the only cases that n could be if it isn't a multiple of 3. So we've proven it exhaustively. Therefore, if n is an integer and not a multiple of 3, then n squared is not a multiple of 3 either. We can now go on and think about the actual year 13 proof proper now. So proof per contradiction, let's have a little introduction to this. It's a powerful proof strategy, and it's usually applied when there's no direct algebraic proof of a true statement or theorem. It's also used if there's no obvious way to approach it directly. Okay, so if you're not sure where to go to, proof by contradiction is a powerful tool to pull out if needed in difficult times. Proof by contradiction, it always follows the same general procedure though. And so what we do is we have a true statement which we need to prove. So we've got a true statement. Assume the negation of that correct and true statement to be true. The negation, I'll explain in a second. It's essentially the opposite. So you've got your true statement, you deliberately come along and say, aha, it's not true because, for example, blah, blah, blah. So now we assume the negation is true. And we think, okay then, so if that were true, and deductively work towards proving this negation to be true using known facts and results. So we're going to try and get the negation of the true statement to itself be true. And what you will find is, despite using sound logic, after assuming the negation to be true, we will end up eventually with an absolute nonsense statement which can't be true, or what's called a contradiction. So if that happens, but the steps we've followed since assuming the negation were true were solid, deductive, and mathematically logical, then those steps can't be wrong if it's based on logic. But if we end up with something that is non-logical, but all the steps after the initial assumption that the negation was true, if all those steps since then were definitely solid, then the only conclusion must be that the assumption that the negation is true must have been wrong. If the negation is not true, the original statement must be true. So it's actually a bit to get your head around when you think about it deeply enough. So it's essentially this. Deduce that if using correct logical steps after assuming the negation to be true ends up with some nonsense, the reason has to be the negation itself wasn't right. If the negation isn't right, the initial statement must have been true. We were wrong to have ever doubted it with the negation. So this negation thing, what is it? I did say I'd go back to it. Well, the negation of a statement, it's best thought of as the minimum requirement of a minimum case that would disprove the true statement. And it's very important to think of it as the minimum case only. So consider the example, all children like ice cream. Pretty much virtually all do, of course, but myself included. But not everyone does. So this would be proven false if we discovered all children disliked it. So it's tempting to think maybe a negation is all children don't. However, you could prove this statement to be wrong if just a few children disliked it. Because if just a few didn't like it, if a few don't like it, that doesn't mean all do. But the bare minimum requirement to disprove it would be if just one child existed that didn't like ice cream. Therefore, for this statement, the best negation would be of all children like ice cream is there exists at least one child that does not like ice cream. And negations are formed based off what the original statement actually is. There are 4 main types of statement, to my mind, keeping it as simple as possible you'll encounter. And so there's 4 main negation structures to consider. Here they are. So sample statement structures and negation forms. 4 different types, 4 different colours. So the first type, imagine the statement, it is true that blah blah blah. This is the simplest case. The negation of that is just to say, well, it's not true that blah blah blah. So an example of that might be to say there are infinitely many primes, or the primes are countless. That is negation simply, there are a finite number of primes, or the primes can be counted on a list. A slightly harder example would be, if A is X, then A is Y. So what this means is shorthand really. So if A has some property X, then the same value or same representative A will also logically therefore have the property Y. So if something has a property X, then it also has this following property Y. So an example of a negation form might be, there exists some A such that A has property X, but because it has property X does not have property Y. An example of this might be for all natural numbers, if n squared is even, then n is even. So in other words, if n is a natural number and n has a property that n squared is even, then it's saying that n will also have a property that n itself is even. That would have negation that there exists some n such that n squared has a property of being even, but does not have the following property of being odd. So like x is a property of being even and y is a property of being odd. A third type would be at least one of elements A and B have this property x. A negation of this would be there exists some A and B such that neither have property x. So to put it into words to make it clearer, it might be if P times Q, if the product of P and Q is even, then at least one of P or Q is even. That would have negation that there exists an even product PQ with neither P or Q having the property of being even. The final negation form I'd like to consider is that some element of a set has both property x and y. That would be proven wrong most simply by the negation there exists some element A such that A is either not x, or it's not y, or it's neither of x or y. So an example might be people in my town have a property of both being rich and happy. That would be proven wrong by something along the lines of a negation. There is at least one person, remember not all or even a few, just one person in the town who has either not have a property of being rich or not had the property of being happy. Or could have also said or neither rich nor happy, of course. So those are the sample statement structures and negation forms which you need to be familiar with, and we're now going to practice a bit now and a lot later in 1.1b. So, proof by contradiction. Let's have a couple of warm-up examples, really. Worked example 4. Then 1.1b, we'll hit proof by contradiction again in more depth. But for now, proof by contradiction that there is no smallest rational number greater than 0. So you need to get ready for a bit of writing. First of all, let's assume that there is some smallest rational number. Let's just call this capital N, say. Since n is rational, let capital N be A over B, because that's how any rational number can be defined, as one natural divided by another natural, where A and B are both greater than 0. So a natural number can be thought of as a positive over a positive. Sorry, a rational number can be thought of as a positive over a positive, even if B happens to be 1. So we've defined n as being the smallest possible rational number that ever could be. However, if you can now consider the number of a value n over 2 would be a over b divided by 2, which should be a over 2b. Element a has not changed, but element b has become 2b. But since b is an integer, or a natural number we could say, then 2 lots of b is also a natural number. And that goes back to that idea of closure we mentioned earlier. You don't need to write down as z is closed under multiplication. So this bit here is optional. That just shows, I suppose, more depth to the examiner that you really know your stuff. you can just leave it as, since b is a natural number or an integer, 2b has to be an integer or a natural number. Because of that, of course, like we've said, since b is a natural number, then 2b is a natural number. So for that reason, n over 2 is also rational. However, very obviously, n over 2 must be less than n. Since dividing any rational number by 2, that reduces its magnitude by a factor of 1/2. If divided by 2, it's going to be only half as large. That, of course, contradicts our assumption that there exists some smallest positive rational number, capital N. Therefore, there exists no smallest rational number greater than 0. You can always think of a rational number smaller than one you define. If this is the smallest, how about a over 4b? How about a over 8b? So again, you can never get the smallest possible rational number. There's always going to be one smaller you could think of. A final worked example before we close for the day, and then think about 1.1b afterwards. Worked example 5. Prove by contradiction that there is no greatest odd integer. Again, this is really easy as long as you keep your head on and start from a logical initial step. So, assume that there is some greatest odd integer that can ever exist. Again, just call it capital N. Call it capital whatever you want, really, as long as you're clear and consistent. So, because n is odd, let's define the greatest odd integer in existence to be n as 2k plus 1, where k is some natural number. Now, if we consider the number n plus 2, that would be 2k plus 3. And again, there's a few ways of clearly demonstrating that's going to be odd. If you wanted to, you could factorise out the 2, then write it as plus 1. Or you could just write it out with words. Since n is odd, n plus 2 is also odd, because a number 2 greater than an odd number will also be odd. Of course, on the number line, odds alternate. Every second number is an odd, and every second number is an even. So, n plus 2 is odd. However, of course, just state the obvious, n plus 2 is greater in magnitude than n on its own. And so n plus 2 is an odd number and greater than n. But what did we assume to begin with? Well, we assumed n was the greatest odd integer. So therefore, this contradicts our assumption that n was the greatest odd integer. Now conclude and we're done. Therefore, there can exist no greatest odd integer, because whatever odd integer you think you've found, I could always add 2 to that number and say, well, this one's also odd, but 2 bigger. And so we'll leave it for there and pick up a bit more proof by contradiction next. And the warm-up will be based on proving that there are infinitely many prime numbers, which is a classic proof going back to antiquity. So, as I say, we'll leave it there for today, and thank you very much for watching. I hope this has been of use to get you a bit more confident with the proofs which will be coming up. So, until next time, until the next video, I'll see you all again very soon.